Please make him feel welcome, Mitko Oldfield.
Hey guys, so with my presentation I made it pretty audio-visual, so sorry in advance for people at the back that can't see the visual part, but luckily I'm upsettingly loud, so hopefully the audio part is not too bad. So we had two presentations already about the very large, which were very good. I'm going to be talking about the very small, and it's going to be very mediocre. One other size-related thing as well, I did do some funky little animations. Some of you probably won't be able to see the ones at the bottom, but I can just try and describe it to you. We'll see how it goes. Could be terrible, could be good, I don't know. This is my first time public speaking. So, my name is Mitko. I am part of Fleet, which I will explain, which is funded by the ARC, which I will not explain. And I'm going to be talking about these things called Polariton superfluids. And you might be like, I have absolutely no idea what either of those words mean. Guess that's where the presentation comes in, eh? So, modern technology, phones, laptops, etc., etc. Most of you know that these things rely on circuits. Within these circuits, we have transistors, and the whole function of a transistor is basically you have a current flow through it, and it gives you a 1 or a 0 depending on whether or not it flows one way or the other. The 1 or 0 then translates to binary, and then you have a bunch of them going off at once, which gives you the basis for code. Modern technology, yada yada. The thing about transistors at the moment is they're not doing the best job. I mean, they're doing all right, could be doing a little bit better. So I'm kind of going to break it down into two main parts. There is the transistors themselves, which you guys at the back definitely didn't see the funky animation for, and the wires as well. So, if we swing it back to 1975, we have this dude known as Gordon Moore. And Gordon comes up with this thing known as Moore's Law. And Moore's Law, in its essence, is that less is more or less. And what I mean by that convoluted statement is the less space that's taken up by a transistor, the more transistors you can have in a given area. And the more transistors you have, the more computations you can do per given time frame, the faster things are. But he didn't really say that. What he actually said was something along the lines of the number of components in an integrated circuit will double every 2 years. And this kind of translates to something that's known as a semi-logarithmic law, but that doesn't really matter. Basically, we can plot it as a straight line, which is pretty convenient for us. And people took this and they kind of ran with it. And it wasn't really a law, it was a little bit hand-wavy and kind of a hypothesis, if you will. But because everybody in science is tryhards, they decided to try and keep up with it, and we kind of made it a law by being a self-fulfilling prophecy. If we have a little look at that bad boy, you have transistor count on the y-axis and year on the x-axis, and we see that it pretty much follows a straight line. Now, the eagle-eyed, or pedantic, as it may be, among you, may notice that it's not actually technically a straight line. There's sort of a straight point. The thing about Moore's Law is it's more guidelines than actual rules. Shout out Pirates of the Caribbean. So, what we can actually do is we can plot what's really happened. And what we see, you guys can definitely not see the years down there. I can't see it, but my eyesight is tapped. Around the middle section, where you see the spike, that's in the late 90s and early 2000s, where they found out some new architectures, some new innovations. They kind of just went ham with it. They're like, this is pretty good. The problem is they ran out of these new architectures, and you'll notice that it kind of starts falling to shit a little bit as we get to recent years. And you may be wondering why that is. Good question, audience. So, what happens is, I will take this plot that I have nabbed from online because I am lazy, and you also can't read that, good God. Okay, so what we have on the y-axis is the transistor size, and you'll see that it's getting smaller and smaller and smaller and smaller. And what we can do is, because we're scientists, we can extrapolate this bad boy out, and we'll notice that we hit about 1 nanometer, or 4 to 10 atoms, depending on which atom you're looking at, by the year 2027. That's pretty bloody small. So there's a real big problem with this as well. The smaller we make transistors, the harder it is for them to work. Because essentially, classical physics starts falling to shit. You have things like leakage current and other quantum effects that basically make transistors harder and harder to function. And like Intel and all of those have been trying to find ways to circumnavigate that, but it's kind of beating around the bush a little bit. They're getting down to about 2 nanometers, but they don't really know where to go from there. Kind of a big problem. There's also a second big problem. The world supply of silicon, which is the basis for all circuits at the moment, is probably going to be going bye-bye by the year 2030. We are using it up at an astonishing rate, and there is a lot of silicon that is just not going to be reusable. We've used it for circuits, we can't really reuse it, no one really followed the reduce, reuse, recycle policy, so we kind of need to think of an alternative. That's problem number one, that's kind of the transistors themselves. If we then go to problem number two, that's the wire problem. If you guys remember your year 9 physics, or whatever year it is, I'm from the UK, I don't know, the year system's slightly different, but we'll set it 9. You will remember that current can flow by an electron traveling through a circuit, and that electron flows from point A to point B. A little bit like so. The problem is, as it flows from point A to point B, it twats off of atoms and it generates heat when it does this. This heating is obviously not very good. You'll notice that your phones and laptops warm up, but it's also a little bit worse than that as well. So, if we take that circuit, we take our electrons flowing through it, beautifully demonstrated by this thing I've made, you'll notice that the circuit begins to heat up over time. And all of these circuits around the world are actually going to have a tangible effect on global warming, regardless of whether or not the input power is renewable. So it's all well and good using solar, using hydro, whatever, but it doesn't really matter if we're still generating heat and still damaging the environment. Not particularly fantastic. So, this is where I get onto data centers. Some of you may not know what data centers are. They're basically giant servers, / buildings with a lot of servers. And what we find with data centers is that, like phones and laptops, they generate a lot of heat, but because there's a lot more of them, they generate a lot more heat, to the point where they're making microclimates in their own area, and it's all not very good. We also notice that we use a lot of energy to try and keep these data centers cool. About 43% of data center energy is actually used to cool servers themselves. I know it says on the pie chart power provision systems, but we'll put that in quotation marks and throw that to the side because that doesn't really add to my point. So, I've got a couple of fun facts because I needed fillers because my presentation ran short a little bit. Fun fact for you, 1,278 exabytes, or I think that's a billion petabytes, a lot of bytes, basically, of global data is stored in data centers. You might be wondering what sort of scale that is, because it's a bit ridiculous. No one can really quantify that. To give you something to quantify it, all words ever spoken by humanity accounts for 5 exabytes, and we've got 1,278 of those bad boys, if we go by current calculations. Some other fun facts for you. Data centers in Australia alone use more energy than all Coles and Woolies stores combined. And if we then take cryptocurrency, specifically just Bitcoin, no other cryptocurrencies, we find out that Bitcoin mining uses more energy than the entirety of Denmark, which is quite a spicy meatball. I mean, meatball's more IKEA in Sweden, but you get the point, Scandinavia. So, in 2015, along comes this dude called Michael Furrer. Very, very nice guy, met him in person, spoke to him a couple of times, actually had wine at his house. He has the silky smooth voice and charismatic demeanor of a late 90s cult leader, and I would definitely drink the Kool-Aid that he is providing. I mean, I kind of did. It was alcoholic Kool-Aid, it was wine, it was very good. He has a big wine cellar, I'm a big fan. So, there's this question posed. How do we make effective dissipationless, that means no heat loss, transistor devices using quantum scale physics? To which Michael says, say no more. And he starts, yeah, all right, it's a pun, I get it. Groan all you want, it's good material. I know my audience, filthy scientists liking your puns. So, he starts this thing called FLEET, which is the ARC Center of Excellence in Future Low Energy Electronic Technologies. But because no one can be asked saying that, we say FLEET. It's a bit more funky, it's a bit more jazzy, it rolls off the tongue. So, FLEET itself has 3 main goals, / themes. Illustrated by these here. Theme 1 is topological insulators, and for those of you that can't see the GIF, I'm really sorry, it's quite a cool GIF, I didn't make it myself. What you basically have is you have this big-ass bulk material, and what it does is it conducts along the edges rather than through the material. The reason it conducts along the edges is because you have much less resistance along the edges, and it leads to a bunch of interesting states and interesting effects. But also, I'm not going to talk about it more because it's not one of my themes and I don't really care about it. I care more about theme 2, which is exciton superfluids, and theme 3, which is light transform materials. So we will yeet and delete that one and throw it away because I don't care about TIs. And we'll focus on the other two. Now, if we go back to our wonderful circuit from earlier, what we can do with this circuit is we can make it not have heat loss by using zero resistance or dissipationless technology. And we can achieve that technology by using something known as superfluids. So the whole idea with superfluids is that there's no wasted energy because you don't have resistance. Problem is, they need incredibly cold temperatures to form. For those of you that can't see that, that is minus 270 degrees, or about 3 Kelvin. Pretty bloody cold, you're going to need a jacket, phones and laptops, it's going to be a bit of a struggle carrying them around. Not particularly ideal, not particularly useful or handy, we kind of need to think of an alternative avenue. So, this is where Polaritons come in. The first word of the title slide, I finally get around to that point. That was a lot of intro, I know. So, what are Polaritons? Good question again. You guys are really just knocking out the park with these questions. Polariton is made when you take something known as an exciton, which is an electron and hole pair. If you guys can remember hydrogen atoms, you basically have a positive and negative thing spinning around each other, having a jolly old time. Pretty soon, you also said jolly old time, Avi. I've kind of just nicked your phrase there. Anyways, what you can do is you can take a particle of light, or if you guys remember, a photon, and you can throw it in. And if you yeet it hard enough, the idea is that it will stick, it'll do something called coupling, and you will have one single particle, or quasi-particle, this is technically not a particle, but close enough, called a polariton. You might be asking why polaritons are useful. So, the thing about polaritons is because they're made of light and they're made of matter, they have some very interesting properties. Because they're half light, they don't really weigh that much, and because they're half matter, they can also interact with each other. It's kind of the best of both worlds, like, it's pretty ideal. And what that means is they can actually form these superfluids at room temperature rather than the super cold minus 273, 70, whatever it was, degrees C, which is good. But, sorry, I'm using this mouse and clicking about all over the place. We form these polaritons in systems, but it's not quite as simple as just throwing light at an exciton and just hoping it sticks. It's a little bit more convoluted than that. And it requires something called a strong light matter coupling, which is where you have this photon actually bonding, quote unquote, to this exciton, and then the two become one, and all is well in the world. To make it all well in the world, you use something called a microcavity structure. And what that basically is there's layer upon layer upon layer of semiconductor. It doesn't have to be semiconductor, but in this case we'll call it semiconductor. And what you do is you have this semiconductor and you throw it in between these two things called DBRs, which are distributed Bragg reflector stacks. And the whole idea then is they essentially act as glorified mirrors. And what you have is you'd throw a photon in the top here, oh that's kind of helpful that it's got a silhouette, and it would like ping about between these two. And the idea is it would ping about quite a few times and it would eventually stick to an exciton and you'd have these polaritons form, which is good. The problem is, these microcavities are super complex architecture and they require nanometer precision. And what that basically means is they take absolutely bloody ages to grow, because we currently grow them using something known as epitaxial techniques, and yeah, it takes a while. It's also very expensive if this clicker is going to work. There we go. Jazzy gif of cash money. Yeah, not so great. Takes a while. Pretty expensive, all in all, a little bit of a convoluted procedure and not really translatable to the real world. But I'm just going to move the mouse, this is really upsetting me. Now it should be fine. Okay, so, what we can do is we can use these things called Perovskites, which have the chemical formula labeled up there, but no one's going to read that, no one really cares about it, they have some structure and they're pretty cool. The good thing about perovskites is that they can actually form polaritons at room temperature, And the better thing about Perovskites is they can use a process known as spin coating, and it means that they can actually be deposited directly onto this bottom DBR stack, or glorified mirror. So what you can do is you can take your Perovskite, I can't point far enough, but like the far left, you take your DBR stack, you throw on some Perovskite, that Perovskite goes on top, and then you can throw a little teeny tiny bit of silver on there as well, and it forms something very similar to that microcavity before. The good thing about it is, one, it's pretty fast, and two, way cheaper. The downside is the coupling's not as strong, but you can kind of like weigh up the good and the bad, and this works out significantly better. But you might be asking, how do we actually know whether or not Polaritons are formed? Because it's all well and good having this microcavity being like, oh yeah, we got Polaritons, but we don't really know that until we use this system. Well, we can use multiple, but the one I care about, we can use a system known as terahertz time domain spectroscopy, or terahertz TDS. I'll basically explain how that works. What you can do is you can take your sample of interest, whatever it may be. Could be a traditional microcavity, could be a perovskite, could be a leaf, don't really care. You can then take a terahertz probe, and the idea is you throw this terahertz probe at the material, and the terahertz propagates or passes through the material and interacts with it. And if you have the right interactions, what you'll essentially see is the terahertz that comes out is not quite the same as the terahertz that goes in. And if you minus one from the other, what you can do is you can see a change in what's known as the conductivity. We have a cute little plot of it right here. On the up axis or the y axis, you have the change in conductivity, and along the x axis, you have energy. And this is kind of like a plot of conductivity of an ideal microcavity structure. It's not one that I've done, I'm not good enough for that. It's what I'm kind of hoping to see though. And you'll notice that there's two main peaks. There's one over here at around 9 millielectron volts, and then there's another one down here at about 18. If you look at the first peak, that corresponds to these excitons, if you remember, these electron hole pairs that are orbiting each other. But if you've got everything right, you've got that special source in your microcavity and your photons to stick into your excitons, you'll also see this second peak, a little bit higher in energy, that corresponds to these Polaritons. And the whole idea of my PhD is that I want to yeet this terahertz at a microcavity that I've made, because I'm egotistical like that, and see this Polariton signature. This is what I want to see as an end result. I know it doesn't look super exciting, but for me it's like, whoa. It's like those simulated black holes. It's just like, this is some spicy stuff. So, to kind of like briefly summarize, what I want to do, form a stable Perovskite. That may seem quite trivial, quite easy, but Perovskites are kind of a pain in the ass because they react with air, they react with light, they react with kind of everything. It's what makes them good, but it's also what makes them bad. I then want to put that Perovskite on that distributed Bragg reflector, the glorified mirror, and then I want to throw all of that in my terahertz system, and then ideally see that Polariton signature. And then from there, so it says profit at the bottom, it's some dumb 2011 meme, but hey ho. To kind of reiterate on step 5, we first see the Polariton signature, and then the idea from there is we will form the superfluid, the thing I was saying about from earlier, wherein you have this low resistance and you can have stuff propagate through a system without this wasted energy, without this wasted heat, without contributing to global warming. You can then combine that with the theme 1 that I binned off, wherein they're talking about these transistors. Combining the superfluids, combine the transistors, and put all of that into modern technology or future technology, scale up to commercial manufacture. From there, hopefully the planet will die ever so slightly less than it was previously, and I can feel very smug, as can my centre, and we will hopefully get more funding. Thank you for listening. Does anybody have any questions?